It compares input signals to a bunch of other signals and say if it looks like them. Like, that's all it does.
That's it.
Also, sorry if the audio sounds weird right now. I just moved to England and the room I'm in hasn't been treated yet, so I might be flanging like Marauder. But I'm making this video for mainly 2 reasons. The first one being, Law knows how many textbooks expect you to be a math wizard beforehand, and if you don't understand it, they just kill you.
Why the bloody hell do I need the tail series to understand this thing?
And the second one being, while I think the intuitive approaches still work, and the video by 3 Blue 1 Brown is really good, thank you Grant, I love you, I still think that video jumps the gun a little bit on certain aspects, and expect it to be a bit more math literate than just someone starting out. Don't get me wrong, I still love this video and I would suggest you go check it out, but I just couldn't understand it myself the first time I watched it. And so my hope with this video is to give a cool middle ground. The idea is that you understand the building blocks that make up the DFT and how the output is acquired. While I do try my best to explain stuff like Euler's identity and formula, I would still suggest further reading because I'm not gonna go that deep into them. They're more gonna be used as tools to derive what we want, rather than the use case in the wider scope of mathematics. I will give some resources at the end if you're into that, but just know I'm not gonna go that deep into it. I'm also not gonna get into the real issues we face after getting the output from the DFT, but by the end, you'll find out how you can hear me up about that as well. I also wanted to test out Manim for the first time, so here we go. The prerequisites being you know about sine and cosine, and I'm not really gonna go over sampling theory and how an audio signal becomes a digital audio signal, but to give a little bit of a refresher, audio signals are made up of infinite values that computers can't really understand, and so we have to break them down into little pieces called samples, essentially the same thing as how frames exist for a video. If you want a more in-depth introduction into sampling theory, then I do talk about it in this video over here, but if you want an even more in-depth and even more straightforward introduction, then I'd recommend this series and this page as well. Actually, no, like specifically this page, please. Arguably this whole video is inspired by this page, so go check it out so I don't feel bad for practically stealing being inspired by it. You also do need to know what the DFT does, which I'm taking for granted you do if you're watching this video, but just to be clear, it takes a mixed signal with all the different frequencies and separates them so you know what frequencies compose the signal. There are more use cases, but I'm an audio person, so that's just the context I learned it for. Actually, saying the Taylor series has nothing to do with this formula is factually incorrect, because if you were to look at the normal Fourier transform, you would see that you would need the Taylor series to understand how it truly works, even before going to the discrete form. I can't believe you're going in the discrete form instead of going with the Fourier one first, because how would you do that mathematically? You're making a discrete in the entire face of mathematics, and I hope your YouTube channel gets banned, and I hope you get killed. I think what is arguably the hardest part to understand about this equation is this complex notation right here. Granted, for most, I'm sure this huge E here is what actually initially scares people, but it genuinely isn't that hard to comprehend once you do. This small e should really be your main concern. This term is essentially all the different sinusoids we're going to use to compare our main signal to, called X event. Side note, the brackets are squared here because we're dealing with digital, discrete signals with a finite number of points, in contrast to what function notation usually looks like. But to understand how this could possibly represent a signal, we gotta look at the circle. And ideally for now, the unit circle, where the radius is equal to 1 unit. We're gonna place the circle on the number line, so the center is at 0. Here we can see that starting from the center, the radius goes all the way to 1 on the right and all the way to -1 on the left, making a 180-degree axis turn. And maybe if you already know a little bit more about the usual ranges of a sine wave, you might already see an interesting observation here, but we're not quite done yet to call it quits, because we still can't verify that the unit circle is exactly 1 unit vertically. I mean, you could kinda see it, but it'd be nice to have some exact value just to make sure. And we'd also want to keep intact the rules of the horizontal number line, whereas multiplying a value here by -1 would result in the negative value of that number. And multiplying that number again by -1 would do the same thing. Essentially, we would need an axis that's sort of a midway point between this 180-degree rotation across the center of the number line. But if this is the line of all existing real numbers, then we'd kinda need to make something that's not real for our purposes. In fact, we can even call them imaginary. Now I'm gonna pause right here because before I even delve into this, just keep in mind what I'm gonna say is a fact, and for now not something to really understand. It's kind of like saying the car is red or pie is well, whatever. Or E is also whatever. This actually comes up later. Or the fact that you still haven't subscribed yet, which is a fact. So, why not make an opinion? I, or J depending on the literature, I'm going to use J actually because in the context of audio, that's more what you're going to see it as, is equal to the square root of -1. And this number existing as a tool, but not quite a quantifiable number, is just something to take for granted for now. There are some extraterrestrial math that exists and science that has an even more semi-concrete definition of how it came about and its implication in the wider universe. In fact, in researching this video, I stumbled upon this Veritasium video and this whole series on imaginary numbers by Welch Labs. I haven't watched this series yet, but according to the comments, it convinced a lot of people to do math degrees of all things, so he must be doing something truly inspirational over there, I don't know. But by taking J at the square root of -1, it solves the problem that we had earlier of creating a vertical middle ground point, and that's really all we need. If we multiply 3 by J, then we get 3J, and we can place it right here. If we then multiply 3J by J, thereby multiplying the square root of -1 by the square root of -1, we just get -1. And multiplying -1 by 3 gives us -3. And we can see how if we continue on this road, we'd get back to 3 by repeating the same amount of steps. So please, I beg, understand that J being equal to the square root of -1 is less important to us in this case than the fact that multiplying J by itself gives us -1. It's a bit of a tongue twister, but I think you get what I'm saying. But admittedly, I've gotten a bit ahead of myself and created a bunch of literally called imaginary numbers just to prove that this circle does in fact have a radius of 1 around its entire middle point. But this vertical line is rather important if we want to somehow represent a signal using this circle. And to do so, we'd have to go to our sine function. Now what I do next might be elementary for some, but I think it's worth doing just to refresh our minds of sine and cosine. But instead, in the case of periodicity, and how this somewhat janky rotation between J is actually kind of important. Take out a calculator and make sure it's in degrees first and input a 0 in the sine function. You'd be sure to get a 0. Now clear everything and repeat this for the numbers 90, 180, 270 and 360. Your output should look something like this. 1, then 0, then -1, then back to 0. And this repetition would go on forever. Take a screenshot or write this down to remember this, but now we're going to go through the exact same process but for cosine instead. And our output for the numbers that we had before, 0 to 360. We should get 1, 0, -1, 0, and back to 1. Almost like our sine function, just starting one number later. And if we squint our eyes, this behavior is also sort of similar to the repetition that J had, but kind of vaguely. In particular, the sine's output aligns perfectly with whatever the sign J is currently on, or if J is even present at all. What could it all mean? Actually, again, before going forward, I kept it in degrees because it's what we're all familiar with, but to also understand the DFT, especially this part right here, and a lot more other stuff going forward in math and science, we use radians around these parts, okay? We use radians. This is the degrees to radians conversion right here, but I'll just say that 180 degrees is equal to pi radians. Thereby, you could surmise that 0 degrees is equal to 0 radians, 90 is equal to pi divided by 2 radians, 270 is equal to 3 pi divided by 2 radians, and 360 is just equal to 2 pi radians. No, wait a second. And it goes without saying, if you had your calc sang for calculator in radians mode and swapped out the degrees with the equivalent radians, you'd get the same answer. Okay, cool, radians done, woo! Notice how up until this point, I've been talking relentlessly about the behaviors of the trigonometric functions, but we haven't mentioned the titular triangle once. Well, I did a little bit earlier, but And while they will show up soon, I kinda don't want you to think about them in relation to these functions, as I think it lessens the real essence of what these functions have to offer, them being a perfect representation for periodic movement. But for now we're gonna look at the behavior of sine. I would actually like to do cosine first because then we wouldn't have to deal with imaginary numbers just yet, but I think sine gives a way better visualization from the get-go for what's gonna happen. And what's gonna happen is that we're gonna rotate a point along a circle by an angle that we're also gonna input to our sine function and track its output over time right here and on a separate axis. And once we stop, we get a sine wave. And while that does make sense, it is the sine function after all. Notice how the output we get from our sine and on the axis is exactly the same as whatever the y position of our point is. And to harken back to our little exercise from earlier, while this is in radians, we can see that we get the same infinite rotation between 0, 1, 0, -1 and back to 0. We never go above 2 pi radians here, but we don't really have to, so just don't worry about it. We could also ignore the whole j part for now, it's gonna come up soon enough, but it's kinda cool that we can represent sine like this. Of course, if we speed up the rotation of the point or vector, we would get a higher frequency. And if we were to slow it down, a lower frequency. I mean, it's literally tracing the output of whatever y is. And while we're at it, if we shut down this whole operation, do a little rearranging of our scene, and do the exact same thing for our cosine function, we'd get a cosine wave. The output we get is the same as whatever value on the x-axis our point is at. And to also give a bit of definition on why a cosine is called a phase shifted sine wave of 90 degrees, or pi divided by 2 radians, look where our wave starts for both of them. The first point of the cosine starts at 1, which is equal to the value we'd get for our sine wave at 90 degrees or pi divided by 2 radians. In fact, we can see on our rotating vector here that we're already at 1 without rotating anything, far less pi divided by 2 radians. Thereby, cosine is ahead of sine by pi divided by 2 radians. I've said pi divided by 2 radians a lot in this paragraph. While that's all well and good though, a spinning arrow traces us waves, we still don't really have anything to directly call the point, rather than its relative position to the x and y axis respectively. But why not describe it like that? This point here, which for our purposes we're going to call z, is the result of going a certain distance right on the x-axis and a certain distance up on the y-axis. This number, being made up of a real number and an imaginary number, is called a complex number. But let's say you wanted to walk from the center of the circle to this point here. You wouldn't want to go how many paces right, then how many paces up. It'd be way shorter to just know how much to rotate from the center and just walk straight to that point. And we know it'd be shorter because the hypotenuse of a triangle, while being the longest side, is never longer than the sum of the other sides. And well, wouldn't you know it, this diagram forms a triangle. Finally, we have a triangle, which kind of goes to show that maybe learning trigonometric functions in terms of triangles kind of limits what we think their use cases are a lot. Like, we only get to them now, like now. Maybe we should have learned triangles in relation to this. I mean, that would have helped me a lot in my studies, I'm not gonna lie. But since we are dealing with a triangle now, we could easily work out the length of this vector here by finding its hypotenuse using Pythagoras' theorem. Also, a vector is just like a line with a direction. This is a vector, this thing is a vector, there's a line with a direction. Okay, cool. Now, admittedly, to use Pythagoras' theorem, we do have to know the lengths of each side, but since we're in a unit circle, we kinda already know that this hypotenuse is just gonna be equal to 1. And we can break out how we learn trig functions using good old SOHCAHTOA, taking the tan inverse or arctan, and we should get pi divided by 4 radians. It's like pi divided by 2 radians, divided by 2.
Calc is short for calculator.
And again, even though we don't know the lengths per se, because we know they are the same, this fraction here would just be equal to 1. It's also 45 degrees, and radians is really the better unit we should be using, but if this video is the first time you are using radians, then I understand it's a bit of a weird shift, but just get used to them going further. I'll convert them for this video, but just get used to them going further. And while we now have a quantifiable way to measure the rotation and the length of the walking needed, how could we portray it in a single equation like the rectangular form? Well, meet... Wow, in 2018. So E is actually, like I said, equal to all of this. It's like pi. They're both irrational numbers where the decimal points just go on for infinity but don't repeat. This E is actually used in a lot of things, but for today we're going to look at a cool aspect of this number. What's cool about E, apart from its derivatives, is if we were to put e to the power of j pi and add 1, we'd get 0. This is called Euler's identity. This E is actually called Euler's number. This equation is supposed to be one of the most beautiful in all of mathematics, so like, don't ever bring it next to your girl, I guess, I don't know. I mean, it is a kind of cool equation. Because using our big brain mathematical minds, we can easily see that this has to be equal to -1, because that's the only number we can add 1 to get 0. But imagine that this pi exponent is actually an input, and in this equation is just a hard number of pi. We know something else, that when inputted pi into its function, we get -1. And in fact, while we're at it, if we were to add the output of the other function that we know to that output, we'd still stay at -1 since the output is 0. And thus, Euler's equation is born. E to the power of j theta is equal to cosine theta plus j sine theta. And this equation has all kinds of implications for our circle over here. Now, we don't yet know what the length of these sides are numerically, apart from the fact that they are equal since we're on a 45-degree rotation. But let's say we wanted to find out this here y offset. Then we could take the cosine of pi divided by 4 and use the hypotenuse to find our missing adjacent. But wait, our hypotenuse is just 1. So our adjacent really is just cosine pi divided by 4 radians. And one could also guess the same thing would occur when dealing with sine. And now it's exhaustingly clear that in the case of a unit circle, given Euler's formula, all we need is the angle the point is at to determine our adjacent and our opposite, which we can now instead more sophisticately call our cosine and sine respectively. As for non-unit circles, however, while this does seem like an issue at first, it makes complete sense to just define the point at the unit length and multiply by whatever magnitude we need. Thus, we now have two versions to represent our point, which are called the rectangular and polar coordinates respectively. And this act of referencing the same thing, but with various representations, is the heart at which the DFT uses to represent the signals we saw earlier. Moreover, now that we finally have an equation to represent the point on Euler's number, we can start piecing together this whole mysterious part of the DFT itself. Okay, I'm recording this little part in just to give a little bit of an answer of why sine has a j in front of it, and it's just because of the fact that on the complex plane, the y-axis is imaginary, and Euler's equation maps to the complex plane. That's it. There's no deeper meaning of why sine is imaginary. It's just the fact that sine is akin to the y-axis on the complex plane is imaginary, and Euler's equation maps to the complex plane. That's it. Don't think too hard about it. It's just a representation. That's all you have to get into your mind right now. Okay, we can go back to the video now. This e to the power of -j, etc. looks just like a polar coordinate if we just extract all of this as theta. And as for the negative here, it's just a convention, and all it does is instead of rotating counterclockwise, it rotates clockwise. It literally doesn't change anything really interesting about the DFT. The only difference is that the sine wave is now negative, but that doesn't really change anything important to us right now, so just don't think about it too much. But for this extracted theta, it's kind of hard to explain what it does without mentioning the big guy over here.
Why sigma mills are more attractive than alpha mills. Stay tuned.
Welcome to the Anthony Spade channel.
It's a for loop. Essentially, it sums up a bunch of values by saying, okay, you're gonna sum up this variable here, this is equal to what at the start, and which variable to go to, okay, go, go, go! Okay, I know it's kind of funny, but it really isn't that hard. Just, if you want, just like slow down the video, but it's not that hard. But there are more than one variable over here, so we're gonna break down what they mean. K is equal to what frequency we want to see is present in our signal. Capital N is the number of samples in our input signal. Let's say we had a 1-second clip of audio at a sample rate of 44.1 kilohertz, which, harkening back to earlier as I talked about samples, would mean that 44,100 samples are taken every second. Thus, there'd also be 44,100 samples in our 1-second clip. So N would be equal to 44,100. Small n is equal to the current sample of the complex sine wave and our input signal, and 2 pi is a representation of a full cycle in radians. Let's say we're trying to figure out if frequency 3 is present in a signal that is 7 samples long. Then what we're gonna produce is a complex value that is equal to the cosine and negative sign of the input theta. You could think of this E-complex notation as a function that outputs the current value of the cosine and sine wave we are using to compare. Now we only have 7 points from this E-complex notation because the input is only 7 values. Now this does have certain implications, but we're going to get to that a little bit later. We will then, according to this equation, multiply whatever value is at the nth sample of our index to the cosine sample, while simultaneously to our sine sample as well. If small n at this point was 0, then it'd be the sample at index 0. But according to this equation, we do that for every sample in our input, which as said earlier was 7. And so we do the same for sample index 1, 2, 3, all the way to 6 since we're 0 indexed. And now for each one, add all of those products together to get a value for our real and imaginary parts. And of course, written together like a complex number, we now have the final output of our DFT. Okay, but then how does this tell me how much of a frequency is present in my wave? Well, remember, this is a complex number, so it's just another point on our complex plane. The magnitude of an existing frequency is the same as the absolute value of the magnitude of any point on said complex plane, which is essentially just saying Pythagoras' theorem like we did earlier on the side of the triangle, which we can now sophistically call our imaginary sine and cosine. And that's how the discrete Fourier transform works. To go over it one more time, we have a frequency we want to see if it is in our signal. We produce a complex wave, which is really just a cosine and sine wave with that same frequency. Mathematically, all of these points are just increments of the tip of a rotating vector, which each produce its own sine and cosine value. We then multiply whatever values at the current sample of our signal to both the cosine and sine values for all the samples in our signal and add all of them up to create an output consisting of a real part and an imaginary part. The real part being the result of the cosine wave and the imaginary part being the result of the sine wave. We could then extract the magnitude of the frequency in our signal and the phase that the frequency is at in our signal. Now you might be pondering, how do we even know what frequency 3 is? And as a matter of fact, how many frequencies do we go over? And for the real astute of you, you might be wondering, if we have to create discrete points for samples, wouldn't we also have to make discrete frequencies to test? The answer to that is yes, and the number of frequencies we test is equal to the number of samples in our input signal. And whatever frequency we're on, so let's say frequency 3, can be found out by using this equation here. We multiply the frequency index by the sample rate of our input divided by the number of samples in our input. And so I'll leave off with a couple of questions to ask. If we were to plot out all the frequency indexes starting from 0 to n-1, we would get a plot of frequencies that are mirrored at the front. Why is that? And if each frequency value we get is a discrete value that increments by a certain amount, what would happen if our signal had a frequency between said increments? To give somewhat of an answer to that last question, I'd like to direct you through this window filled with resources, starting with my Patreon. Okay, so the discrete Fourier transform is a pretty broad topic to understand, and it takes a while to explain too. Like, I planned this video to be 10 minutes long. That was the original plan. And so as much as I'd love to go over everything, I can't do that without this video being even longer than it already is. So while you do have enough knowledge to understand what the DFT does and how it operates, if you want to go even deeper, then you can check out my Patreon, where you'll get some extra content that explains fully how the DFT works, all of its properties, and how we deal with, frankly, a lot of the faults that it has. Such content will be in the form of a continuation of this video, along with a code walkthrough on how you can make your own DFT implementation from scratch using Python. If you're watching this video in the future, the code for that walkthrough will probably be in the description of this video for free access. But if you want a full walkthrough done by yours truly, all of the Blender files and Manin project files I used to make this video, and further explanation on how we deal with all the issues the DFT has, and getting this kind of content for every successive video I make, then click the link in the description. To show my gratitude for the first cohort of members, you'll get access to all of the perks of all of the tiers for just £3 for the first 10 members. That's less than a protein drink at my gym. I'm not even lying. So if you want to know more about the DFT, its properties, and its flaws, click the link in the description. I will say, if you go to the Patreon right now and you say, well, I don't see the walkthrough, all the extended content, it's coming in a week's time. I just got over chickenpox, so the content had to be delayed a little bit, but in a week period from when this video drops, you will get those videos. Probably even before the week period ends, most likely, but just expect it in the week period. Granted, if you do want to learn more about the math covered in this video specifically, we have the Veritasium video and the Welch Labs series linked as well. There are a plethora of online resources as well if you've come this far and you realized, wow, this guy sucks at explaining things. They've all been linked in the description as well. Some free, some paid for, but you'd get an alternate explanation of things. And finally, please go check out this page by Jack Schaedler. I hope I'm pronouncing that right, but please go check out that page. I think this is the standard we should try to attain to display these topics, and I do hope I'm able to keep up the good faith of this purpose of showing technical DSP and audio stuff in a straightforward manner with my videos going forward. But if you want to learn more about nerdy audio stuff, specifically more on the sampling thing and how we really get that mirrored output after a certain frequency, then check out this video here.